All right, awesome. And we are live. Welcome to the Cool Data Project Show. I'm Kristen Kerr, a developer advocate for Comet, and this is the Cool Data Project Show, where I interview practitioners in ML, DL, and AI about interesting projects that they're working on with a focus on methodology and approach. And today I am speaking with Neeraj, who is going to talk with us about the robustness of ML models. And so, Neeraj, would you like to introduce yourself?
Yeah, sure. Thanks a lot for having me on the show. This is a great opportunity. I'm kind of excited to talk about some recent work of mine. So I'm a PhD student in the Department of Bioengineering here at the University of Illinois. I kind of stumbled into bioengineering. My background is also on the computer engineering and the statistics side. So a lot of my research for the past couple of years has been about at the intersection of brain-related disorders and machine learning. So what we try to do is we try to sort of use domain knowledge from the clinical side and try to develop sort of machine learning tools that can help in sort of various healthcare applications. For example, diagnosis of disorders, prognosis, and things like that. So that's the general sort of area that I work in.
All right, awesome. And so, what was the motivation for this project? What are you trying to solve?
Right. So a lot of the work in sort of machine learning and deep learning, typically focuses a lot on building sort of new and better models. But what we are seeing sort of in the field and like practical usage is that despite really good performances on the training set, these models break in deployment. And partially this is because of changes in the dataset distribution compared to what the model was trained on. So really the motivation was to not just evaluate model performance, but kind of think of performance in a more holistic sort of fashion. So in this project, instead of focusing on building new models, we are really focusing on improving the evaluation of models that are already trained. So that's kind of the motivation of the work. That if if we are able to somehow sort of predict or see early signs of failures of a model during the development stage itself, we can avoid potential failures when these models are deployed. So the goal of this project is to kind of build sort of a diagnostic tool or a sort of a heuristic tool that can tell model developers, okay, that this model is very likely to fail in practice. And we kind of leverage a lot of domain expertise in brain signals to sort of make this sort of tool. Yeah.
Yeah, awesome. No, and I'm excited to talk about this because, I remember working on my master's in statistics, we'd talk about robust estimators and stuff like that. And then
Right.
in industry, I really don't feel like I hear about robustness a lot and making sure that a model is going to do well once it's deployed. So,
Right.
how are you collecting your data? What data are you using for these projects?
Right, right. So the data I mostly work with is basically electrical brain signals. They're called, the tool is called electroencephalography. And these signals are sort of, the shorthand is EEG signals. And so what happens is electroencephalography is like a very versatile clinical tool. So if you have an exam, they'll put a grid of electrodes on your scalp, and they'll start recording your brain activity. And what happens is each sensor gives you a time series. So if you have a grid of sensors, you get like a stack of time series, and that's essentially what these EEG signals are. And we kind of know that these brain signals, they contain sort of rich information in sort of time, space, as well as frequency. So that's kind of the data that we're working with. So as far as the project is concerned, we needed sort of two data sets in order to mimic what developers will actually face in practice. So on one data set, they have access to during development time, right? So that's the data set that the models are going to be trained on. But to sort of validate our approach, we also need to show that our tool can sort of predict performance failures on an sort of real world data set, like an in the wild or out of sample evaluation. So that's so we use a second data set for that. So both of these data sets are publicly available. The in sample of the training data set comes from Temple University here in the US. The outer sample, or sort of in the wild evaluation that we perform in the study, it comes from a sort of a military hospital in Pakistan. So it's kind of like halfway across the world. But we kind of use these two data sets to show that the idea works. Yeah.
All right, awesome, very cool. And Scott says hello. Hi, Scott. Hope you're doing awesome. And Alex mentioned that he is doing something similar for his work in NLP. All right. So, and what is the methodology that you're using here?
Right. So, so the method in this project can be sort of broken down into 3 steps. So let me start with what the hypothesis is, and so what's the problem setting that we're exactly dealing with. So the hypothesis in this study is that if you don't have any knowledge of the target setting in which a model is going to be deployed, the latent space of the encoder itself may sort of give you some early clues as to how the data might shift. So the idea is to first, in sort of as step 1, try to construct sort of transforms that capture sort of realistic shifts. And for this, we rely on a lot of domain knowledge. So we sort of go to domain experts and try to get insights on how exactly the signals change from one hospital to another, from one subject to another, and so on and so forth. And you can sort of encode these shifts as transforms that can be applied on raw data sets. So since you don't have access to an external data set, you can kind of synthetically construct one based on these transforms. So that's step 1. Step 2 is about sort of passing these 2 sets of data that you have. You have the original data, and now you have a transformed version of that data. And that transform has been synthetically constructed in step 1. So you kind of take these 2 sets and you pass them through the model that you want to evaluate. And you get 2 sets of embeddings, sort of 2 point clouds in the latent space. So in step 2, what you can do is you can somehow measure how close or how mixed these point clouds are. And the intuition here is that if these point clouds are well mixed, that means the encoder is sort of more robust to the transform. But if the encoder sort of really segregates these 2 point clouds away from each other, that's going to lead to problems downstream. So so using this sort of a measure, we call it an integrity measure. Conversely, you can consider it like a distortion measure. You can get a sense of how sensitive your latent space is to transforms that are applied at the input. So step 3 is you kind of push those embeddings 1 layer ahead. Typically, we find that neural network architectures, you can kind of think of them as just like an encoder and a linear layer on top. So step 2 was at the output of the encoder, and then step 3 is at the output of the linear layer. So that's your predictions. So you can do something similar in step 3, where you can say that, okay, how much does my prediction vary if you were to get an uncertainty estimate from your model? And then you can compare the changes that happen under the transform in step 1. So those are kind of the 3 broad steps of the methodology. And the constraint here really is that somebody just hands you a trained model, right? And now you're supposed to kind of evaluate it and sort of give some sort of insight on whether how robust is this model. So depending on what sort of transforms you pick in step one, you can say that, okay, at least I can say that if these transforms occur in like the out of sample data set, at least I know that my model will be fine. So that's the overview of the methods.
All right, awesome. And so is this all time series neural nets?
Yeah, that's right. So so the data is multivariate sort of time series, and we sort of compare three different types of models in this project. So one is a typical sort of convolutional network that's trained in a fully supervised way. The second is a self-supervised approach, and that doesn't use any labels for training. So it's sort of how language models are kind of pre-trained. Similarly, there are some EEG specific sort of pre-training tasks that you can train a model using. So that's the second sort of model, and the third one is kind of a classical baseline in the EEG field. So that's just about looking at the spectral content of the signal and sort of extracting power from the signal bands. So we compare kind of the robustness profiles of these three encoders using those three steps that I mentioned. Um, yeah, yeah. So this is neural network sort of models mostly, and we assume that they have kind of a very general structure where you have the input X, you have the encoder that's sort of going to give you embeddings, and on top of the embeddings, you have a simple, say, a linear layer for classification or regression, and that gives you your predictions. Yep.
All right, awesome. And so what kind of like challenges or difficulties have you experienced working on this project?
Right. So one of the challenges is so shifts in the real world, they don't happen in isolation at like one at a time. They're kind of multiple shifts happening at the same time, and these shifts may kind of interact in complex ways. But in our approach, we had to kind of make a simplification that, okay, we just assume one type of shift is going to occur. Uh, and we were able to find a validation data set where we could try to fix as many factors of variation as we could, and only have the variation that we're trying to test, just to make the experimental design a bit more clear. But I think the general case is much more complex, and I think we kind of need to we may need different strategies to handle an even more realistic scenario where you have multiple shifts happening at the same time. I think one of the other challenges was in each of the three steps that I mentioned, you kind of have different sort of modeling choices. So, for example, latent space analysis in step two is a field of its own. It has a bunch of methods that you can use. The field of uncertainty sort of quantification has its own sort of methods. It's an active area of research. So we had to make a reasonable choice to demonstrate that the composition of the steps kind of gives you a good solution, rather than focusing on making the perfect decision for each step. So if you had more time and in follow-up work, we are interested in sort of doing more comparisons. That, okay, if we use method A versus method B for step two, what changes? And so yeah, I think that was one of the challenge where every step has a lot of decisions that you kind of need to make. And it is really there's not always time to do all of the comparisons that ideally you would want to see.
Mm-hmm. Yeah, so it sounds like you're working on a whole bunch of little pieces. What are you working on like right now, and what you'd like to tackle next?
So this approach, the scope of this work was to try to identify model failures as early as possible during model development itself. Uh, and I guess the next natural question is like, okay, now that you've identified the failure, can you tell me how to fix it?
Mhm.
It wasn't done as part of this study, so it's a very natural extension that we are working towards. One of the things is that in step one, when you apply these transforms to the raw data, these are actually applied when you're evaluating the model, not actually when you're training it. So the natural question that arises is that okay, if you apply these same transforms during training, does your robustness improve?
Mhm.
So that's kind of one very obvious direction where this work could be extended. Um, the second is that the type of shifts that we model in this study, they're really focused on hardware related changes to the EEG signals. But really, if you think about the broader sort of spectrum of shifts that healthcare settings can have, you can have the population of your data shifting. You can have changes in the clinical protocol that's being sort of conducted from one hospital to another. You can have the subject sort of physiology or sort of biological changes happening in the brain. And all of these, change the signal a little bit. And if the model is not kind of robust to any of these categories of shifts, you're going to run into issues in deployment. So just increasing, sort of the set of shifts that you test on is also, one direction of future work for this project. Yeah.
Okay, yeah. And so this is something I know nothing about, but you mentioned hardware. What type of hardware are you doing, and what sort of, if there's an improvement, what are you looking at in terms of like changes?
Right. So for example, there's different sort of manufacturers of EEG hardware across the world, and they make certain sort of decisions in sort of the electronic circuitry itself. So, for example, they may say that okay, as soon as a signal comes in from the patient, they're going to sort of bandpass filter it, uh, and then they're going to store it in a digital form. Um, Now, the issue is that different manufacturers choose to use different settings for the bandpass filtering. So the spectral content of the signal might vary a little bit from one instrument to another. Second, when the sort of clinician is putting this grid of electrodes on your scalp, they need to kind of ensure that the contact between the electrodes and the scalp is clean. And sometimes, and many times, it's not. So that changes how the signal sort of manifests for the data scientist who's kind of developing these models. Another example is how precisely is the signal amplitude being stored. So if this sort of EEG hardware is very resource constrained, they may choose to sort of quantize the signal to a lower number of bits to sort of save memory. And again, that precision might affect the modeling that you do downstream. So these are the kind of effects that we are expecting to see, and those are the effects that we modeled in step one of this paper. Yeah.
And so you're tracking the precision and like of the different hardware.
Right. So what we do is we say that okay, if you take the precision as a data set shift, we induce varying levels of varying levels of the shift. So say 6-bit, 8-bit, 12-bit, 24-bit, for example. If you consider the bandpass filtering step, we don't point to any particular manufacturer, but we just construct shifts with multiple sort of extreme values, like different levels of extreme values. So with bandpass filtering, you can have sort of a very liberal sort of range of frequencies that you permit, or you can have it very restrictive, the frequencies that you permit. So we don't really compare or keep track of specific manufacturers, but we just look at the shifts at a conceptual level and then create at varying degrees of extremities these shifts. and then we test the model with each of those levels. And then see how it does. I think one of our results, what we found was that any sort of signal related noise, like impedance noise or broadband noise, any extreme levels of those can significantly degrade model robustness. The quantization sort of effects and the bandpass filtering aren't as bad for the neural network models, but especially the impedance and the broadband noise tends to degrade the model significantly.
Interesting. So you've like tested all these different things. How many different like ways do you think you've pressure tested this model?
Right. So I think we've kind of pressure tested 3 different models in 4 categories of shifts. But all of these 4 are related to the instrumentation of the EEG device. So that's kind of the scope of our sort of analysis so far. So yeah, we've stressed 3 models and 4 different types of shifts. And what we find is that the sort of fully supervised encoder, it actually performs better in terms of traditional model performance metrics like AUC, accuracy. If you look at metrics like those alone, you would conclude that okay, fully supervised sort of network is great. But it doesn't turn out to be as robust as the self-supervised one or the classical domain baseline. So there's kind of it seems like our results suggest that maybe there's like a trade-off here, with absolute task performance and the robustness of the encoder. And that's an interesting sort of trade-off that's worth exploring further. Yeah, that was one of the things we found.
Interesting. Yeah. And so robustness is obviously something that could extend to lots of different areas.
Yeah.
Can you share off the top of your head, do you know like how other people might want to go about doing this?
Yeah, absolutely. I think that's a great point. And I think it's one of the sort of the advantages of this approach, that even though I'm talking a lot about brain activity and sort of healthcare, like you correctly said, these shifts occur in like NLP, in vision. The shifts occur everywhere, and this approach can kind of be adapted for other settings as well. So I think the adaptation mostly takes place in step 1, where you define these realistic shifts and sort of implement them on raw data. So there you're going to need domain experts from that particular field to construct these transforms and make sure that they actually reflect real world variability. So if you're able to do that for other domains, then I think this approach in step 2 and step 3 can still work just the same, because we don't assume, apart from the transforms, we don't really assume anything is specific to brain signals or EEGs. You can pick any encoder that you like in vision, NLP. You can sort of perform the same analysis. Yeah.
Awesome. Is there anything I haven't asked you about your project that you'd like to
well, I think the maybe like the takeaway message of this project is that you don't always need data from like a target setting in order to evaluate robustness. So we show that in a very constrained setting where you just have access to your model and your training set, and you have some domain expertise, you can kind of exploit that to sort of give you an early sense of how your model might fail in practice. So we don't really depend on external data sets or expert labels to sort of conduct this robustness analysis. And especially in healthcare, getting these labels from clinicians or doctors is very expensive. So we don't get a lot of those. We try to make use of the labels that we currently have and sort of any unsupervised sort of approaches, um, that can be constructed. So I think that will be maybe the takeaway, sort of the take home message for this project. Yeah.
Mm-hmm. And then, so if somebody wanted to get, study up on being able to evaluate the robustness of their machine learning model, are there any resources that you think they should check out?
So that's a good question. I think the first sort of task here when trying to evaluate robustness is to kind of define robustness against what,
Mm-hmm.
right? So that would be a good starting point. And there's this one field of adversarial robustness where, instead of using domain expertise to construct shifts, you can kind of algorithmically construct or synthesize sort of data. So that might be an interesting sort of area to look at too for robustness evaluation. That so just synthetically construct these variations and see which one of them makes your model fail. So if somebody can find a way to sort of implement those type of approaches for their data set, I think that would be a good start.
All right, awesome. Yeah, and then for the person who wants to just start with ML, that it's brand new, do you have advice for somebody who's looking to get into the field?
So this is an interesting question. So I mean, ML is like very composite field. It's not sort of
There's a lot.
yeah. So I think in sort of like a jack of all trades approach might work best in the beginning. So if you start with all the classical sort of foundations of machine learning, like statistics, optimization, sort of algorithms, and so on, I think sort of getting the basics there first would be a good start. I can see that there may be like a temptation to just dive into all the latest and the greatest stuff, but I don't think that's very useful for learning if you're new to ML. Yes, that would be one. The second would probably be to stick to like toy data sets. You typically don't want to sort of take on all the complexity of the real world when you start learning. So it's maybe just best to stick to like toy data sets and resources that show you kind of both the theory side and the practical sort of programmatic side of things as well. I think that helped me quite a bit. I would recommend those type of things for somebody starting out.
That's a good point, because I see on social a lot of times you'll see a meme or something where they're talking about, toy data sets versus the goriness of the real world, and people can sometimes maybe look down a little bit on those toy data sets, but they really do have a place in terms of allowing people who are new to like easily start to grasp and not have to deal with a million things, right? They're just
exactly.
fitting a simple algorithm. Yeah, no, those are really important.
Yeah.
So if somebody wanted to find and follow you on the internet, how would they go about doing that?
So I have like an active Twitter account, and I also try to post resources related to my work on GitHub. So I think those two profiles, I think they should fairly easily pop up with a Google search. But I think those two places would be a good place to find me. Yeah.
All right. Awesome. So thank you so much for joining me today. I really enjoyed hearing about your project and about, robustness in general. I can think back on my own experience, and I've built models and, maybe checked on it in, first time period, second time period, third time period,
Right.
just to make sure it's a little consistent. And that's literally about as far as I've gone. So this was, really interesting to hear about how this is your work and all the different things that you're considering. And thank you so much for joining me.
No, thank you for the opportunity. This was really great conversation, and yeah, I'm happy to share what my work is about. Yeah.
Yeah, awesome. Well, thank you everyone for joining. I hope you enjoyed this episode, and I will see you soon.